Okay, in this set of videos, we're going to discuss classification, sometimes also referred to as pattern recognition. But classification is a specific type of pattern recognition because basically what we tend to do is we tend to try to cluster data into different classes or categories. In bioengineering, a lot of times we're looking at determining a specific disease or a condition from some range of measurements or other diagnostic data. So that's one application of classification. So classification is applied to a pattern of descriptors, and the measurements are the input space. It finds a class or a category which best fits each pattern. Most biomedical engineering problems involve a small number of classes, sometimes only two classes. For example, you have the disease or you don't have the disease, your tumor is malignant or it is benign. There are a couple of exceptions. One thing that comes to mind is Alzheimer's disease. In Alzheimer's disease, you tend to have more of a range, and sometimes if you're working with older adults, you're actually looking at three categories: normal, um, mild cognitive impairment, or full-on Alzheimer's disease. So that would be one exception where the classification would be done sometimes with three classes. In addition to that, there are sometimes other forms of dementia that might even form additional classes. So it's not always two, but often it is two. I do want to comment very briefly about sort of the standard in healthcare. Typically, pattern recognition techniques are new on the scene when it comes to standard of care in biomedical applications. Typically, if you read the publications in the healthcare literature or the biomedical literature, they still are using statistical methods. So you basically are doing some kind of a statistical test like an ANOVA to determine whether or not two categories of data are different. Pattern recognition adds a new twist, but it's not necessarily viewed by the community as reliable enough or traditional enough to have entered the actual practice of medicine. So that's something to keep in mind. If you look at papers, you'll find the classification algorithms published in the engineering literature. You still do not see that many publications in the biomedical literature that involve classification algorithms. Some, and more than there used to be, but still ANOVAs and other statistical tests continue to be the gold standard. So classification attempts to associate a pattern of input variables, sometimes these are referred to as features, with either a specific class or another variable. So if the output is another variable, the analysis is referred to as a regression. If the output is a discrete number that identifies a specific class, then the analysis is referred to as classification. So what classifiers do is they establish a relationship between an input pattern and a discrete output. And they can be viewed as mathematical functions, and classifier development can be thought of as a function approximation, or identification, estimation, or pattern recognition. So all of these terms are used sometimes with different subtle nuances of meaning, but typically all of these terms are used. So here's just a block diagram of what was previously discussed. You have your classifier, you have some inputs, you have some free parameters, and then your output basically identifies class. Typical outputs can be plus or minus 1 or 0 or 1 or 1, 2, 3 if you have more than one, more than two categories. So the inputs are also often referred to as features. They're something that you've calculated from your data set. Typically they are not raw data, although they can be, but they are typically not raw data. So part of the biomedical signal processing role here is to take the data set, do the appropriate signal processing, and come up with a set of features. So for example, when you did the project on the EEG and you found EEG power in different bands, those would be potential features that would be input to a classifier. The free parameters are typically something like a weighting scheme. where the different inputs are somehow sorted and weighted, and then the output, once again, would be the class or the category. So there are two types of ways for a classifier to learn how to classify data: supervised and unsupervised. So in unsupervised learning, basically the classifier will try to find patterns within the input data with no a priori knowledge of any data patterns, and perhaps not even a knowledge of the number of classes or categories that actually even exist. So this is unsupervised learning. In supervised learning, the classifier is trained. So you take a data set for which you know the correct class, and then you use a training data set that includes the correct answers, in other words, the correct classification. So both of these strategies fall under the general heading of machine learning. Supervised learning is typically the most common approach in biomedical engineering applications. During training, the free parameters of the classifier are adjusted to minimize classification errors, and this can be an iterative process. You use a training set where the answer or the correct classification is known for each pattern. The classifier performance is evaluated then using a validation set for which you also know the correct classification, but it's not used to modify classifier parameters. And the idea is that this classifier should perform with minimum error on data it has never seen. So just one comment about a training set of data. This is actually much more difficult than you would think. So for example, when I used to work with groups that did Alzheimer's disease research, we would be pretty sure, maybe 95% sure, that the individual who was diagnosed with Alzheimer's disease actually had Alzheimer's disease. But there is always some uncertainty in medical diagnoses, which is part of the reason, of course, you're trying to get a more data-driven approach to diagnosis. But that makes coming up with a 100% known training set, it makes it a little bit difficult. Same is true, of course, obviously, with the validation set. Furthermore, when you make biomedical measurements, especially if you're working within neurological systems, and also with cardiovascular, if the patient is medicated, the medications themselves can influence the outcome of the measurement. So, for example, with heart disease, if that individual is on a beta blocker, it can actually change the waveform of the EKG. If individuals are taking ADHD drugs or benzodiazepines, it can change the EEG. So not just finding a training set, but finding a group of people, even if the diagnosis is 100% accurate, who aren't taking drugs that alter the measurement, can also be quite challenging. So when the training is complete, basically the classifier is applied to a test set where it performs its function to determine the most likely condition based on a given data pattern. And then basically the classification error that occurs during your testing phase is the one that really matters. Now, one common problem with classifiers is that they will perform well on the training set, but then they do poorly on the test data, which is the real-world application. So we say that those classifiers generalize poorly and or they are overtrained. Sometimes people will say that the data set has been overfitted. So here's a typical classification done based on two variables. Now this can be generalized to n variables because basically the mathematics is the same. It's just n variables, but two variables, we can plot one against the other in a scattergram, and we can clearly see that one group sort of clusters down here in the lower left-hand corner, and the other group clusters up here in the upper right-hand corner. So we have two descriptive variables or features, and clearly we can see we have two classes or categories. So if we wanted to somehow separate these two classes, we can come up with a decision boundary that separates these two classes based on their positioning, their physical location in the scattergram plot. So in this case, if we just draw a line like this, then that's a decision boundary. Coming up with a good decision boundary is important because that's part of what makes the classifier perform well or not well on a set of test data. So the decision boundary and the definition of how to achieve the decision boundary is important. If a straight line or plane or hyperplane can completely separate the classes, then they're said to be linearly separable. So a plane would be if we had 3 variables. A hyperplane would be if we had more than 3 variables. Now, although classifiers might deal with a large number of input variables, it really is easiest to visualize them when you're only dealing with 2 input variables. So the examples shown here use 2 input variables, but keep in mind that you can have quite a few variables. Now, there is kind of a practical limit on the number of classifier variables that you want to use related to how many samples you have. So if you only have a group that has, say, 12 normals and 12 diseased, then you wouldn't want to use 12 classifier variables. And pattern recognition people would have a much better rule of thumb than I would, but basically you certainly don't want more, say, than 25% classifier variables or features of what your total pool of test subjects is. Now, there's not really a limitation on the variables, as the classifier methods that are described here extend to multiple inputs very easily. All right, here's an example of another data set, variable 1 versus variable 2. And it's clear when you look at that these variables are clearly separable, but they're not separable by a straight line. So clearly they cluster into 2 groups. And it's very easy just by the eye to see that they're 2 very different groups and that it's easily separated by a boundary, but the boundary is not a straight line. So these are separable, but they are not linearly separable. Okay, and then here's an interesting data set. And this is what happens if you overtrain or overfit. So in this case, the classifier has come up with a very complicated looking boundary, pretty much based on this one point here in blue, possibly on this one as well. So the classifier is told that this is a member of the round blue group and that these guys are members of the black square group. So it knows that they need to be separated. So by going through multiple iterations, a separation boundary or a classifier boundary is come up with that looks like this. And so because of this overlap, this slight overlap in classes, to really get them to separate, and you can imagine, that there could be other points over here that would make for an even more complicated boundary. So if this is a training set, the boundary probably will not generalize well, and this boundary is probably too complex. And here's an example of what can happen. Okay, here's our training set. And if we use this complicated boundary, then we take our testing set and we can see that on our testing set, we actually have a number of errors because obviously your testing set and your training set are not the same set of data. So if you do have, and once again, the Alzheimer's disease example is an excellent one because Alzheimer's actually occurs over a range. And so you may have some people who do not have Alzheimer's disease who have features that look like Alzheimer's disease for whatever reason, but they're actually not a part of the group that would be classified as having a disease. Then your test set, you would also expect there to be some overlap just because of the physical part of the problem. So you can see that if you use this complicated boundary that overfit the training set, you have 3 errors in your data here. On the other hand, if we had done a simple linear separation and allowed ourselves to have an error on the original training set, then with the test set you actually get a better fit You only have 2 errors here, one misclassified in each group. So the complexity of the boundary is determined by the classification algorithm. And since classification is part of machine learning, the classification algorithm complexity is termed the machine capacity. So machine capacity is a major design factor of a classification algorithm, and it determines how complex the decision boundary can be. If the capacity is too large for the data set, the classifier will overtrain. It'll perform well on the training set, but it doesn't generalize well and it performs poorly on the test set. If it has too little capacity, it will show excessive errors in training and have a rather subpar performance in classifying the test set. So these are the engineering trade-offs that occur with regard to machine capacity.